And so you've now added this into your notes. You'll notice what's different about this from your previous notes on difference quotient is, first of all, previously all you had was just a formula. It was just, hey, this is the formula for difference quotient, but we didn't know what it meant. Based on the work that we did earlier this week, we built a connection there where we saw that if we want to find the slope of the secant line between 2 points, we can use difference quotient for that. And that's actually why it exists, and we're going to be doing some more work using this going forward here. The basic idea that is this is that x is your starting point. We use a for that as well. You can use either one, but I'm using x here because it's going to make our final result a little bit easier to understand. And the other point is h horizontal units from x. This is the big thing to remember, though, is when we have 2 points, h is not the second point. H is the distance to the second point. And remember, it can be negative, so if you're heading to the left of your original point, h is going to be a negative value. When we go to write the equation for this type of situation, this is how we can make it look. We want to know when the distance above the ground is going to be 450. So we do 450 equals 4.9 t squared. Seeing that, we can now solve for t, because I want to figure out when this ball actually hits the ground. So I want to solve it to see when it actually travels 450. So please solve that equation. All right, and so in order to solve this, we divide both sides by 4.9, take the square root of both sides. By the way, when we take the square root here, do I need to worry about both the positive and the negative?
No.
Nope, because we're just worrying about the time after it was dropped. So we don't care about negative times, that is times before it was dropped. I'm sure that equation would not be the same for it, right? Because we're just holding on to it. So we get an answer of about 9.58 seconds. So it's going to hit the ground in 9.5 seconds, basically. The question that we're asked is to find the instantaneous velocity of the ball for each second until it hits the ground. So basically that's the integer seconds between when it's dropped and when it hits the ground. So I want to look for all of the integer t values between 0 and 9. That gives us 10 instantaneous velocities to find. Now, this would take a very long time to do if we have to make a graph and then hold up a ruler to the graph and estimate what it's going to be for each one. And it's not going to be all that accurate if we do that. So, there's a better way. We can actually use the difference quotient for this. And we'll see how, because if you're really astute at the moment, you're going, wait, difference quotient is for secant line, but this is asking for instantaneous velocity, which is tangent line. That's true, but we can still use it. So, let's go ahead and take our equation here, plug it into difference quotient, and simplify your result, please. So, when we do this, of course we do x plus h squared, and yes, make sure you actually multiply out x plus h times x plus h. That's going to give you x squared plus 2xh plus h squared. Multiply that by the 4.9, cancel out what you can on the top, and then simplify out the h on the bottom. You should get a final answer here of 9.8, there we go, 9.8x plus 4.9h. All right, so now the tricky part with this one. I want to know what the instantaneous velocity is. Yet this equation will only tell me what the average velocity is. Because remember, difference quotient tells us the slope of the secant line. Secant is average velocity. We want instantaneous velocity. So in other words, the slope of the tangent line through this. Well, thinking back to some of that work you were doing before, if we're looking for the slope of the tangent line, it's basically like we have our starting point, and the other point that for the tangent line, it keeps getting closer and closer and closer to that original point. And then it's getting close to being the actual tangent line. What is our h value approaching? 0. And so in order to then figure this out, we can actually then plug 0 in for h. And if h is 0, then the instantaneous velocity can be represented as 9.8x. And so the slope of our tangent line then ends up being just 9.8x.
That's flat.
Now, in order to do that, we actually just use something called a limit.
Wait, is that?
We just use limits to figure this out. But there's a whole notation and a whole school of thought that goes with limits, and that's where we're going to be going with a lot of the rest of today. But that means we got something that needs to go into your notes here. Now, you add this into your notes, and this shows us how we can use this limit notation to represent what's going on. Now, in the last problem, let's see how this would look for that. I wanted to figure out what the instantaneous velocity was at x seconds. We used x instead of t because we were plugging into different quotient there. And what we actually then found is we wanted to know what the limit was as h approached 0. And we had that equation that we had found out, 9.8x plus 4.9h. And so in order to figure out what the limit was as we approached 0, we then plugged the 0 in for h, and so that's why the whole thing ended up equaling 9.8x. That's an odd place for that. There we go. And so we ended up with an equation of 9.8x. Notice what we did there is we actually evaluated the limit. We plugged 0 in for h, and then just saw what it equaled. Now, there will be cases where you can't just plug the number in, and that's what we're going to be doing in upcoming lessons. But on a nice simple equation like this, yeah, we can just plug it in and see what's it approaching as this becomes 0. Having done all that work, this problem is now easy to do. Because we now want to know what the velocity is, remember, at all of the integer values between 0 and 9. Okay, find the instantaneous velocity, please, at each of those values now. So having done that, that was kind of a way to introduce limits and look at what we were doing earlier in the week. I now just want to focus only on the limit part and how different limits can be used. So here's the first problem that I want to take a look at here together. And in this problem, you're actually going to see some different types of notation come up with that limit. So we got our graph that we're given, and all these are related to that. So that first problem, notice what it's written here. X, right arrow, that means x approaching. 3, and then there's like that little minus sign. It's actually written like an exponent. It's a superscript. What that means when you see that 3 and then the minus is that means it's approaching 3 from the negative direction. In this particular case, since it's x, that means we're approaching 3 from the left. So it's basically saying, as you're approaching 3 from the left-hand side here, so here's 3, as I'm approaching it from the left, like this, what number am I approaching? Okay, and so I look to see, what is that y value that I'm approaching there? 2. And so that would be the limit as x approaches 3 from the left-hand side. It would be 2. Okay. Now we go on to the next problem. There we're looking for the limit as x approaches 3 from the right side, that is from the positive direction. So we're following the graph, and as we approach 3, what y value are we approaching? 2. And so that one is also 2. Now, when that happens, when we're approaching the same number from both sides like this, that means that we can actually know what the limit is as x approaches just 3. It's not from either direction, it's from both directions. And so it must be the same as the others. So it's approaching 2. Notice when it doesn't say minus or plus there, it's from both directions. So we have to be able to tell from both and have it be the same. And then for that last one, f of 3, it is just 2. And this one was a nice, easy one because that point was actually just a point on the graph. Of course, some of these change. Same graph, but this time we're going to look for some of those values at 4. All right, now for this one. For our first problem, as x is approaching 4 from the negative direction, that's from the left-hand side. So I look at my graph, and I'm kind of following the graph along as I approach 4. What y value am I approaching? 4. Okay, so there we go. And from the right-hand side, from the positive direction, I'm approaching 4. What value is that approaching? 4. Absolutely. And so then, when I take a look just at this one then, as x is approaching 4, then it must be 4. Because it is in fact the same from both the left and the right. It's equaling that same thing. And so, what does f of 4 equal? 4. Not 4.
Oh, nothing's undefined. It's
that one is undefined, yes.
not applicable.
There is no solution there. And so notice that a limit can then tell us, okay, what value is the graph approaching, even if the value doesn't exist there. Okay, but then even, what if things are just a little bit wonky around that point that we're approaching? Go ahead and write down these problems, and then we'll talk through them as well. All right, so for this one, as x approaches 2 from the left, from the negative direction, so I jump onto the graph and I'm heading towards 2 from the left-hand side, what number am I approaching? 3, absolutely.
Wait, but what about the other one?
Okay, next problem. As x approaches 2 from the positive direction, that is, x is approaching 2 from the right now. This one, it's approaching 1. Now, a little note there. Notice that that answer did not change at all based on whether it was an open or closed dot. I was just following the curve down and seeing what is it getting really close to as I go along. All right, so then, the limit just as then as x approaches 2, well, now we got a problem, because from the left it's 3, from the right it's 1.
That means it's 2.
That means it's undefined. There is no limit as x is just approaching 2 here, because it depends on whether you're going from the left or the right. And it needs to be the same for us to be able to define that. All right, f of 2. What's f of 2 then? That one we do know. Yes, it is 3. That is the only instance where the solid versus open dot actually does come into play. And so since it was solid here and open down here, that means to use this one. So I figure if you got it with the graphs given to you, you can make your own graph. It's kind of tricky and it bends your brain a little bit, but it's good practice with this limit notation. So please sketch a graph that meets these requirements. As I look down this list of requirements, the very first thing that jumps out at me as being kind of easy to deal with is actually the last one. F of 0 equals -1. That's just a point. So I'm going to go to 0, -1 and plot that point. Okay, that's nice and easy. The top one, then, now I got to get into the limits. As x is approaching 0, so in other words, as x is approaching the y-axis here, f of x needs to be approaching 1. Now notice though, that's x is approaching 0. It's not from the left or the right, it's from both sides. So both sides, it has to be approaching 1. So I know I got something coming in there from the left and from the right. I don't know what kind of slant they are at right there, but I do know that. But notice that if I make them go through 1, I'm going to have a problem, right? Because f of 0 is supposed to equal -1. So the only way that I can have them approach that, but have this still be different, is if I then put an open circle there. So we can get an open circle up there that it's approaching, but when we hit it, there's actually a different value. Okay, so that could hopefully take care of the top and the bottom requirements. Now let's take a look at these two in the middle here. So 3 from the left and 3 from the right. So as I'm approaching 3 here, from the left, I should be approaching -2. Okay, so I'm going to go down to -2, and it should be approaching, looks like I'm going to have to be going down in there. I'm going to have something like that. So knowing that alone, I guess from that open circle, I'm going to have to be going down there. I just got to connect those up somehow.
Wait. A function if like x also.
All right, and then the next part, as x approaches 3 from the right, we're got to be approaching 2. So that means I'm up here. And I don't know what it's doing over here. I could go any way I want to on the right-hand side. Now, it is f of x, so we know it should be a function, right? That means I should not have solid dots on both of these at 3. At least one of them needs to be an open circle. Now, you could actually make both of them open circles if you want to, but one of them needs to be open. It doesn't matter which one, but at least one of them needs to be open. And then to finish off my graph, I got this weird little tail sitting out over here. So I'm just going to make that go off, and it doesn't matter where it goes, it just needs to go someplace. And actually, technically, it doesn't even need to go someplace, but it's good form. And so you notice we end up with a piecewise function. So you start by going ahead and writing out each of these so you can then work them through. All right, so now let's take a look at these. So for that first one, we're looking for the limit as x is approaching 2. So notice it's approaching 2. So remember, that means from both the left and the right. So as I'm approaching 2 from the left, we're doing one of these. What's it approaching from the left?
Negative
It is approaching, yes, negative infinity. What about approaching it from the right? That is also negative infinity. Therefore, the answer to part A is negative infinity. But notice that I had to look from both the left and the right in order to be able to answer that. All right, part B, next to it. As x is approaching 5. Well, from the left, it's approaching infinity. From the right, it's approaching infinity. And so, it's approaching the same thing from both sides, so that is our limit. All right, part C. The limit as x is approaching negative 3 from the negative sides. That is, from the left. That's going to be negative infinity. And as we approach negative 3 from the positive direction, that is from the right, that's up at a positive infinity. It didn't ask it, but the value, if x was approaching just negative 3, that would be undefined. Because notice, from the left and from the right was different.
Why is it approaching negative?
The reason why this is approaching infinity and negative infinity is because we have asymptotes in there, right? And so we should then be able to write the equations of each of those vertical asymptotes. So we have one of them here that's at negative 3, so that's going to be x equals negative 3. Remember, x equals for a vertical line. We have one over here at 2, so x equals 2. And we have one at 5, x equals 5.